From this video onwards, we'll talk about tensors. Uh, but before that, I want to mention something from the previous lecture uh, about the definition of the manifold. So, so in the definition of manifold, we saw that it have to be locally Euclidean, Hausdorff, and second countable. We only discussed about locally Euclidean, what locally Euclidean means, but uh, I didn't mention why do you need Hausdorffness or second countability, and what are they. So I want to mention that briefly. So what intuitively speaking, what Hausdorffness means is, let's say we have a set A, and we know there would be elements of A. Let's say there are two elements for all elements xy in A. Let's say two elements xy in A. We if there exist for all element xi in A, if there exist two open sets U and V, such that U intersected with V it gives us in the empty set. So what it means is they are disjoint. If we can find such U and V for all xy in A such that they are disjoint, then the set will be called Hausdorff. Now, why do we need Hausdorffness? So we need Hausdorffness because it ensures that the limit of any sequence is unique. And why do we need this? Because we want to do calculus in our topological space, sorry, in our manifold. And if the limit is not unique, we wouldn't be able to do calculus, because you know that for the limit have to be unique if we for calculus to hold. So this is why we need Hausdorffness. And now what second countability is. Second countability second countability means that the basis of our topological space is countable. So finite. Sorry, countable, not finite. So we need this because you have seen in the previous video that so we've seen that while defining locally Euclidean, you have seen that we need a homeomorphism between our open set in the manifold to a Euclidean space Rn, and we know that Rn has a countable basis. So second countability is preserves under homeomorphism. So this open set U also have to be second countable. So that's why we need this. But there are manifolds without who are not second countable, and there are some things like that, interesting things like that. But for our purpose, our manifold have to be second countable. Every time it will be assumed all the necessary thing, okay. So now I'll talk about tensors. I have already defined it in the previous video, but I'll do it again. So let's say we have set a vector space V. Let our vector space be V. And you know that it will have associated dual vector space. So its dual is v star, and then a tensor of type rs t is the multilinear map. I will define multilinearity after giving this definition. So tensor is a map that takes r copies of dual vector space v stars, and s copies of the vector space, and maps it to a, so it there are s copies of v and there are r copies of v star, and it maps to the real number. So this map is called the tensor. So now what multilinearity means is multilinearity means it is linear in every slot. So let me define a tensor of rank 1 1 1 1 2 0 tensor. Let's say 0 2 tensor, 0 2 tensor. And then let's so our vectors, so two vectors, let's say phi plus, let's say 0 to tensor. Phi usually defines map, so 2 0 tensor, phi plus psi comma plus lambda. Then what linear in every sort means is that you can write it as phi comma psi plus lambda, phi plus lambda plus psi comma plus lambda, and it can be broken down to I plus t of so this is what means to be multilinear. Now let me give some example. So let's consider a 0 1 tensor. So the map will look like v takes one copy of s, or s is one copy of v or vector space, and maps to r. Now from the definition of dual vector space, you know that the dual vector space consists of functions that take an element from our vector space and maps it to the real number, and this map exactly look like that. So this vector, so this function t, in this case the 0 2 tensor is basically a covector. You know that the elements of the dual vector space, those functions are called dual vectors. So a 0 2 tensor is a covector. Now let's consider a 1 0 tensor. So 1 0 tensor will have one copy of v star that maps to r. Now there is a theorem that says now what we can tell from this, that this t belongs to the dual vector space of the dual vector space v, and there is a theorem that says that v star dual vector, the dual of dual is basically the same as the actual the vector space v. So since t belongs to this and this is v, so t is a belongs so a 1 0 tensor is a vector. Now let's say we have our manifold M, and we know that at every point P there is a tangent space. I shouldn't write this like this. So there is a tangent space TPM, which looks like Rn. Sorry. Now we define now we so we want our sorry, not vista, only vista. So only T. So this time we let our vector spaces to be the TPMs. Then the tensor at that point P is defined as T star of M crossed R copies of sorry, not T, yes, T star, R copies of T star of M and S copies of TPM, and maps it to R. And we have already mentioned about the basis of TPM and TP star of M. So the basis of TP star of M are the one forms, and the basis of TPMs are the vectors, or the vectors. Yeah. So in component form, and the TP, it will look like. So we have R copies of TP star of M. So mu1, mu2, mu R, and we have S copies of TPM. So V1, V2, and Vs is basically P. Now we know the basis of TPMs are the one forms. So the dx mu1 at P, dot dx mu R at P, now the basis of this ddx of mu1 at P, dot mu s at P. So these are the basis of the components of the tensors, and physicists usually refer these things as tensors, the component as tensors. Because so in physics books, when they call something tensor, they usually define these components of the tensor, the map tensor. Now let's see an example of a 1-1 tensor. So 1-1 tensor. So 1-1 tensor will have a vector and a vector v. Sorry, a covector phi and a vector v. And we know how to write them. We know we can expand the covector in terms of the basis of the dual space. So, and we have already I have already mentioned in the last video that the basis of the components of the dual vectors will have a contravariant index, covariant index, and the basis of dual vectors will have contravariant index. So this, and a components of vector will have contravariant index, and component of, let me not write this, let's say ij, ii, j, and the basis of the vectors will have a, we'll write it Fe, it will have a covariant index. Now we know, oh, I have forgot to mention on the thing, on the multilinearity property. So here is another condition is if we have a scalar multiple lambda dot phi, sorry, not lambda, let's say psi, then it's basically this, and these lambdas are numbers, basically real number or complex. So here you can see these i's are numbers and j's, phi i's are numbers and vj's are numbers, so we can pull them out and write it as t of, sorry, in terms of the basis, and it looks like this, and these are this, these are this, but here so this is basically, in, if I have to write this in, it has 1 and j, basically only one index, mu 1 and pj or ij normally. So here is I, so it will be and j, so this. So in this case we have so for a 1-on tensor it looks like this. So you can already see, I think this term here makes sense after this example. You get an intuitive idea what this term means. So yeah, oh sorry, not this, they are basically this is, I mean, this is j and this is j, sorry for the, not those, this are the, now let me define a tensor product. Let's say we have two tensor, a tensor A with type Rs and another tensor B with type T and U. Then the tensor product A tensor with B is defined as basically you know that so it will be a R plus S, R plus T and S plus U tensor, type tensor. So in component form, tensor will be the component of that tensor product. So it will be psi 1 sigma 1 sigma 2 dot 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 sigma r, then sigma r plus 1 dot 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 sigma t. So here r plus t uh, indices, and in the down it will have rho 1 rho 2 dot 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 rho s, then rho s plus 1 dot 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 rho v. So here it has s plus v indices. So it is basically this sigma 1 dot dot dot, dot sigma r rho 1 dot 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 rho s, and b has sigma r plus 1 dot 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 sigma t, and rho s plus 1 dot 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 rho v. So basically you just include the basis. Now let's talk about the transformation laws, which is very necessary for calculations maybe. So transformation laws. So let's say A is a 0 to tensor, 0 to tensor, and our vectors, and we have a vector space V, and its bases are Fi's. And one of the you already know that the basis set is not uniquely determined. We can have a different basis for the same vector space. So let's say the usual. So let's say the initial basis was EI's. Now, but now we consider another basis set Fi, which can be whose elements can be written as in terms of the previous basis as Ij epsilon j. So it can be written in this form. Now let's consider our tensor A. So let's say Ajk is equals to. So this is since it is a 0 to tensor, we'll have two vectors and 0 covectors. So let's see, have on vector j and f of k. Now we know that we can expand this fj and fk's in terms of the previous basis vectors. So j, let's say m, em, and a, k, l, el. We know that these are the scalar coefficients, so we can pull them out from. So kl, and it's em and el, which is precisely the tensor EML in terms of the previous basis. so so this so so a tensor follow this kind of transformation rules. We can write a tensor in terms of another tensor using by in with some linear combination of some coefficients. Let's take another example for a 1-2 tensor. So for a 1-2 tensor, let's consider the basis of our dual vector space phi i's, and let's say so let's the basis of dual vector space B star is epsilon j's, and we are considering another uh, basis set phi j's, and we know that we can write the phi j's in terms of the previous vector space epsilon j's with some components. So let's say b, let's consider b since it's some over here. So this is I want to give, so this is j and this is I. So you're summing over I. Now let's take our tensor. So it's a 0, it's a 1-2 tensor. So I, j, and f, it can be written as phi of and normally what we do is write this like this to what do I say? It means that this is in the f basis, and we'll get something like at the end we'll get something like e something and it will means it's in the e basis, but let me put off let me not write this for now. It will be much easier, and it should be obvious from the context. So phi k, fi, and f j. So I can write this as in terms of the previous epsilon m. I can write this as I and m, e of n, and a j, let's l, e of l. Then I can pull off the components I, m, a, j, l, symptoms which is the tensor m and l. So it is related to this tensor by this transformation law. Now let me give a practical example. I mean practical by let's say our vector space is R. Let's say Rn. Then we know in Rn. No, let's say our manifold is M. And our tangent, let V be the no let V be the tangent space TPM. Then we know that the V star will be TP star of M, and we know the basis of these two vector space. So the basis of the TPM is dy dx. I am not writing the P at point P. I mean it's evaluated at the point P, but I'm not writing it explicitly. And the basis of the TP star of M is, let's say, J. EJs are the one forms. Yeah. Now let's consider another basis of TPM and TP star of M. Let's say F I is d over dxi dyi. So it's in a different basis, and EJ is now dyj's. Now let's see the action of d dx of I at point P on F point P. Let me write it. Now this is the partial derivative. So in our now let's consider a chart. So now let's consider so it's our TPM, and we are considering a chart X. Let's take a point. That takes it tangent vector P on the manifold and maps it to a chart X. Let's take another chart Y that do the same, and they are Rn. Now we can write it as d over dxi the function composites with the inverse map of x and evaluated x point x of p. Now now what this means is that now we have a point in this chart, and we are pulling this here, and we are evaluating it here, but so I have already mentioned that we work in charts, not in our manifolds. So this is an example. So we consider a open set U and map this thing to a chart, and we do our usual calculations in the charts. So So this map is, this should be clear from this picture. Now for shorthand I can write it like this. Now let's take y and y inverse. Let's take y inverse and y. And y I'm all gonna tell you now, and it's in our notice that this is identity function, so I can write it like this without worrying about. Now let's use the chain rule. So first I have to consider this inverse, and they are evaluated in y of p, and then chase x inverse one evaluated of x of p. Now I can write this as df of dy yes I can. I'm just skipping one line. You can relate, you can see this looks like this, and you can write this as this. So yeah, which is evaluated at point P, and I can write this using the, it will be xi and yj's. And you can write this yj xi at point P. D of dyi function. So what we have seen that, so d dx of, so which is d dxi on point P. So if I forget about the function and only look at the action, so it will look like d of dxi is equals to dy j's of dxi dd of I. Sorry, I have made some mistake. So it will be xj's, wait, then it should be yj yeah, I did a mistake here. So it would be more convenient if I write it as, so first I so first yes, there would be j and this is I, this is j, so this is I and this is j, and now I want to, by chain rule, this will be j. Yeah, now it's not clear. So this is j and it will be x I and now to the j. Yes, now it's yes j and y object. So this is how these two bases in TP star, TPM is related by these coefficients, sorry, components, yeah, coefficients. And now for a one form, let's take, so we have let's see the action of one form. The action in one form of the action of a one form to a function f. Now we let our functions be vectors, so it can be written as in terms of a basis of xj's. So let's take a d by dx j, and they are related by the another basis of the TP star of m. TP star of m is some coefficients, says j. Now b I j, and everything here is evaluated at point P. So d by dxj. Now the action of a one form is, if I have a one form, if it acts on a function f, then if it acts on a function x, where x is in TPM, it is defined as x this. Here TF takes an element from TPM and maps it to R. So the action can, so I have d over dx j of xi is equals to b I j d y j. It's j, right? Yes. So let me write. Let's choose this to be y. Dy can be written as in terms of dx. So dx was our previous basis, and we are considering new basis dy. Then the whole thing. Sorry for the confusions. Dy I dx j is equals to b I j dx j dx j, and this is bj I Kronecker delta of jj. We know this is 1, so ji is basically dy I and dxj. So one form is related as a basis of a of the dual space, the dual vector space TP star of M is related by another set of bases of TP star of M by these coefficients. So this is all for today. The next lecture I will talk about invariance and give some more examples of tensors. So yeah.